Yeah, good morning, students. So we will start day two of control systems. Uh, Now, yesterday we have discussed about control system, uh, how to define a control system. So that is the transfer function of a control system. And in that transfer function, we have seen how to represent the poles, zeros, and so many other things. And we also talked about open loop transfer function, closed loop transfer function, all those stuff. So let us continue with that. So it was said that okay, transfer function in general form can be written as something like k into s plus z1. This is s plus z2. This can have n number of terms here, and this can be s power n. This can be s plus p1, s plus p2, so on. So this is what a typical transfer function. Now, an example of that could be something like this. So transfer function is nothing but, so you can have it as a 10. So it can be s plus 3. This is s plus 2, and you can have this as s into s plus 4 and s minus 5. So from this, we know that I can able to certainly represent the poles and zeros of this. So you have a pole at the origin, you have one more pole at -4, you have one more pole at plus 6, sorry, plus that is at 5. So this is at 5. So these are the three poles. The zeros are at, it's at -3 and it's at -2, -2. So this is how you are representing poles and zeros using this form. This type of representation of transfer function where you have s plus something, s plus something, s plus something, you can see the coefficient of s is 1 here. In all these cases, coefficient of s either in the factors, you have this s plus 4, s minus 5, and here it is. You can treat this as 0 plus s. You can see the coefficient of s is always 1. This type of representation, whether it is there in poles or zeros, it is like okay, s plus something or s minus something. So this is called as pole zero type of representation. This is pole zero type of transfer function. And whatever k that you have here, whatever that k you have here is, suppose if you say this k is equal to 10 here, I will call this as root locus gain. This is called as root locus gain, because k is usually a gain parameter. So what is this k now? So this k, whatever 10 you have, is called as root locus gain is 10. Hope okay, everything is fine. Just one of you give a thumbs up so that I can make out okay, everything is fine. Okay, fine. That's it. I just want to confirm that okay, I am online. So this root locus gain is 10. So now this is one form of representation, and there is another form of representation where we write this. Here you can see it is still now 10. This s plus 3 is there now, so I'll make this 3 outside. I'll take out the 3 outside, then this will become s by 3 plus 1. I'll take 2 outside, so this will become s by 2 plus 1 divided by, so this s is as it is. I'll take 4 outside, so when I take 4 outside, it is s by 4 plus 1. I'll take 5 outside. I'll just take okay this 5 outside. Maybe for this particular case, let me consider this as plus, not to put you into pressure. Let me make it as plus. So if it is plus, I will just write this as -5. So just to avoid confusion in the first problem itself. So now I took it as s plus 5. So this pole which was there at plus 5 has come to this. So I'll take 5 outside. So then this is s by 5 plus 1. I hope okay you're not confused here. Just to have a clarity, I just made all the poles and zeros onto the left hand side of the s plane. So this is s plane. this is S plane. So this is right hand side, this is left hand side, this is your imaginary axis. So now what we have a different form of representation. Now what is this value of what is the constant value now? The constant value is 10 into 3 into 2 divided by 4 into 5, and this is 1 plus s by 3, and it is 1 plus s by 2. This is s as it is now 1 plus s by 4, and this is 1 plus s by 5. So what is this now? This is a new value. So what is that value? So that becomes, this will be 2, this is 5, this 5 and 5 will go off, you'll end now with 3. It is now 3 into 1 plus s by 3, 1 plus s by 2 divided by s into 1 plus s by 4, 1 plus s by 5. So if you can see here, how did I arrive at this point? I arrived at a new transfer function, new form of representational transfer function by simply making this, whatever you had as s plus 3, now I want to make some s plus 1. So this quantity I want to have it as 1 here. You can see this is always 1. So for that, your whatever 3 here, 2 here, 4 here, 5 here is there, I'm just taking it out and I'm just reforming the value of k, which was there 10. Now it will become 3 in this case. I hope this is correct. This is 2, this is 5, this 5 and 5 will go off. It is now 5. So now, what are the poles and zeros? So okay, this type of representation is called as pole zero type of representation. This type of representation of a transfer function is called as time constant representation. Time constant representation. This is time constant form. You might have seen I have shared with you some terms of control systems, in which if you can see there are two types of transfer functions. One is the pole zero type of representation, the other one is time constant form of representation. This is time constant form. Usually how do we usually write this as is? So this is like, okay, k, no? So this is what we written it as k. This is your pole zero representation. In your time constant representation, I will write it as k dash. It is now 1 plus s tau z1, 1 plus s tau z2. This is s power n. This is now 1 plus s tau p1. This is 1 plus s tau p2. See now, here you are writing it as 1 plus s tau, 1 plus s tau. Of course, this is written as tau z because it is corresponding to 0. This is tau p because it is corresponding to pole. This tau is nothing but a time constant, because we know, no? So tau is nothing but, okay, tau is proportional to RC, which is called as time constant. So that's why if the transfer function is represented something like this, so then it is called as time constant representation. The value of k that comes out here is now called as system gain. So what is this 3 now? 3 is system gain. Correct? So now whereas suppose in this case, so this tau z, how much is tau z here? So tau z here is, tau z1 is, so if I write tau z1 is 1 over 3, tau z2 is 1 over 2, tau p1 is 1 over 4, tau p2 is 1 over 5. Where are the poles and zeros? In this form, the poles are at minus 1 over tau p1. So if it is p1, it is p1. Whereas zeros are there at minus 1 over tau z. Meaning to say, where are the poles now? Poles are there at, what is 1 over of this? 1 over of this is 4. That is, there is a pole at minus 4, minus 5. Where are zeros? There are zeros at -2 and -3. What I mean to say here is the pole and zero positions will never change whether you represent it either using pole zero form or time constant form. Where are poles here? So of course we have one at the origin also. This is like okay, 1 plus this is 0. You don't have this. Of course you have a pole at origin. What is this here? Where are the poles? Poles in this form of representation also, poles are at -4 and -5. Here also it was at -4, -5. Meaning to say, when you are representing a transfer function in pole zero form and time constant form, only thing is that k value, now this was 10, now it will become 3. What is this 10? 10 is called as root locus gain. What is this 3? This 3 is called as system gain. So here this k is root locus gain. Root locus gain. What is this k dash? K dash is system gain. System gain. Please note this. This is how there are two different ways of representing a transfer function. Both are interchangeable. If you are given this, you can find what is this. If you are given this, you can find this. So let us do one or two examples, which is a very fairly easier thing. Assume that you have a transfer function. So let us take it's a first transfer function, which is like 100 into s plus 4 by s plus 6 and s plus 1. So this is what pole zero representation. So what is root locus gain? Root locus gain is 100. Where are poles and zeros? Poles are at -6 and -1. Where are zeros? It's at -4. Can I write its counterpart in this is pole zero form. This is pole zero form. What is time constant form? Time constant form. So it is now 100. Take out 4 outside, then it will become 1 plus s by 4. So take out 6 outside, then it will become 1 plus s by 6. And then take out 1 outside, it will become. So now what is this? So this will be now 400 by 6. 400 by 6 would be 66.66. 1 plus 0.25 yes divided by 1 plus what is 6 inverse? 6 inverse is 0.166 yes and 1 plus yes. This is what? This is the same transfer function but represented in time constant form. So what were the pole zero positions? It was at -1, -4, -6 and -4. This is poles and zeros. Now what was the root locus gain? It was 100. So what is the system gain now? System gain is 66.66. Where are the poles and zeros? Poles are at -1 over 0.166, which is nothing but -6. And other one is minus of -1, sorry, which is minus of 1, which is at 1, sorry, -1. So don't you have poles at -6 and -1? Where are zeros now? There is a 0 at negative of the time constant. What is the time constant? It is 0.25. So what is 1 over 0.25? It is 4. So this minus sign remains here. So 1 over this is 4. So where are poles and zeros? It's at the same position. Only thing that we're going to change is this constant value of gain will become from 100 to 66.6. Since you are writing this as 1 plus s tau, so this is tau z1, tau p1, tau p2. So poles and zeros are now represented in time constant form. So this is one typical change. Usually when you're referring to figures or when you're referring to some equations, you will see either this or this. We should not panic. It will be either of these two. Hope this is fine. Just give me a thumbs up if you are all okay with that. So then I can just move to next. Okay, fine, done. So let me move on to so once we are done with this, so let us see what happens to a transfer function. So assume that I have a transfer function. This is my transfer function. Let us stick on to pole 0 form of representation. So assume that I have 10. This is okay. Let me just take a block which is having 10 into maybe s plus 2 by s plus 6 and s plus 1. Okay, let me just take a negative feedback with HFS as 1. To this, let me just put a dummy block for the time being. Let me take it as 1 and let me just have this. So can I know what is the open loop and closed loop positions? So this is what RFS, this is CFS. So what is your open loop transfer function? Since it is 1, this into this happens to be the same. So it's actually GFS into HFS. So what is GFS? It is 10 into S plus 2 by S plus 6 and S plus 1. Correct? This is my GFS. HFS is 1 because this into this is same this only. So where are poles and zeros? If I write the poles and zeros of this, the open loop poles and zeros, where is the pole? There is a pole at -1, there is a 0 at -2, there is a pole at -6. It is the S-plane representation. Correct? So in S-plane representation, I could able to comfortably write this. So what is closed loop transfer function? Closed loop transfer function. Closed loop transfer function is GFS by 1 plus GFS into HFS because I am doing a negative feedback. So then what will happen to this? This will become 10 into S plus 2 divided by S plus 6 into S plus 1 whole divided by 1 plus again 10 into S plus 2 by S plus 6 into S plus 1. Maybe from now onwards, let us not write this repeatedly. If you have this as your transfer function, that is GFS into GFS, so closed loop transfer function will become 10 into S plus 2 divided by, can you see this term comes as it is S plus 6 into S plus 1 plus this term will come. It is 10 into S plus 2. Correct? So upon simplifying, is this equal to 10 into S plus 2? What is this now? So this will be S square plus 7S plus 6 plus 10S plus 20. So can somebody tell me what is the simplified version of this? It is S square plus 17S plus 26. Correct? This is my numerator. In the denominator, this is your denominator. In the numerator, you have S plus 2. Is this my CFS by RFS? That is closed loop transfer function. Let me know whether this is the closed loop transfer function. Just give me a thumbs up there. That is my closed loop transfer function. If that is my closed loop transfer function, let me try to locate the poles. The poles were there at -1, -6 and the 0 is at -2. So what is the transfer function you have now? The closed loop transfer function what you have now is CFS by RFS. is equal to 10 into s plus 2 divided by, what is that, s square plus 17s plus 26. So let me know the roots of it, because it is quadratic, it is easy to find. I can just do it. 1 degree is only 2, it is 1, next it is 17, it is 26. Now it is now the roots are minus 1.699 and other one is minus 15.30. See now the poles which were there at, so where were the poles? The poles were there at minus 1 and minus 6. This is the open loop pole positions. So once you close the loop, so this pole has gone closer to this. Can you see now it has gone here? It is now at minus 1.699. How about this? This has moved to minus 15.3. So how about this? This remains there. What is that blue color indicating? Blue color is indicating the poles due to those are all open loop poles. Minus 1, minus 6 are open loop poles. The 0 position is minus 2, whether it is open or closed. The moment you close the loop, this minus 1 moves here, this minus 6 goes to minus 15.3. Minus 15.3. So meaning the pole position started moving once you close the loop. So now what we'll do is, let us try to add a pole and try to see what is the effect of it. So this was your original transfer function. Now we will see what is the effect of adding a pole or 0 onto the transfer function. If I add a pole at a position s plus 8, what happens? If I add a pole at s plus 8, what happens to my overall thing? So what is the transfer function? The transfer function now has changed to, so let me write open loop transfer function with added pole. It's now 10 s plus 2 divided by s plus 1, s plus 6, s plus 8. Correct? Where are the poles? Poles are now at minus 1. There is a 0 at minus 2. There is a pole at minus 6. There is a pole at minus 8. I am not writing to the scale. This is S-plane. This is real. This is imaginary axis. What is closed loop transfer function? Closed loop transfer function is exactly s plus 2 divided by s plus 1, s plus 6, s plus 8 plus 10 into s plus 2. This is what you're going to get. Now we need to solve for this. So upon solving, so what will happen to this? So what is the product of this? So you have s square plus 7s plus 6 into s plus 8. So that would be s cube plus 8s square plus 7s square plus, this is 50, 56 s. Next it is next what you have is, so what I have now is this is 6s plus, this is correct. So we have this, it is s cube plus 15s square plus 62s plus 48 plus how much? plus 10s plus 20. So what is this now? It is s cube plus 15 s square plus 72s plus what is that? 68. Let me find the roots of it. So how do I find the roots of it? This is 1. Okay, next it is degree 3. It is 1, 15, 72, 68, 68. Now the roots are minus 1.23. It is now minus 6.88 plus or minus j 2.76. Fine. So now when I add one extra pole to this system, when this was not there, the pole which was there at minus 1 has moved to this, and this pole which was there at minus 6 has moved here. When I close the loop without this, now I have added a pole. So when I add a pole, so this is that extra pole, that is added pole has came here. So now this is the pole position and 0 position upon open loop. Once I close the loop, you can see the transfer function is totally changed. So where are the poles now? The poles are now moved to. You can see now where this has gone. So one of the pole which is there at minus 1 has come to minus 1.23. It is coming closer to this. How about this and these two poles? They have become actually complex now. Can you see now this has become, where is the real part of it? The real part of that is at minus 6.88. What is the imaginary part? Imaginary part is at 2.76j. So intersection point of this imaginary and this real part is here. And what is the other pole? Other pole is at minus j 2.76 and its real part is here. This is that intersection. You have the pole here. So now this pole has come here and these two poles have shifted to become. It is interesting to see, when you are opening the loop, the poles were there on the real axis. The moment you close the loop, these two poles which are on real axis have become now complex. They have become complex. How do you get to know this? You got to know because of this roots of the poles. Roots of the poles will tell you where are your closed loop poles upon closure of the loop. Just have a look at, just make a difference between when you don't had this pole, where were the poles and zeros? The poles and zeros, this is the earlier case, the poles and zeros were at minus 1, minus 6. 0 was at minus 2 only. Once you close the loop without this, this has moved here, this has moved here. Now we actually added a pole. Once you added a pole, it has become so and so. Fine. This is the impact of adding a pole onto the system. So of course this has moved to here and here. That is purely because you have added a pole at minus 8. This is due to 1 over s plus 8. Suppose if this position changes, then these locations are totally depending on where you are adding the pole. Just give me a thumbs up, okay, if you are okay with this. I'm just trying to find out what is the position of your poles and zeros as you are adding a pole to an existing system. We will see in the coming classes how to add a pole in real time. So this is in an equation. I can simply add this extra term, but practically how you want to realize, or why do you want to realize, so those things we'll just learn okay, slowly. suppose to the same system, let me not add a pole, let me add a 0. Let me add a 0 at s plus 3. S plus 3. Let me see what happens. So now if I add S0 at S plus 3, so what is your open loop transfer function? Open loop transfer function now becomes, I hope okay this is like mathematics, but we are trying to relate this mathematics in coming days to an electronic circuit or to an application to find out what is the impact of this on the response of the circuit, all those stuff. It doesn't end there in writing an equation, it just goes slightly beyond. What is the impact of this on the stability of the system, why this is required, all those stuff we'll be just dealing it. So with this, it is now S plus 2, S plus 3, and here it is now S plus 6 and S plus 1. Where are poles and zeros? Poles and zeros are at, this is at minus 1 and this is at minus 6, and I have a 0 at minus 2 and one more added 0 at minus 3. Fine. This is S-plane representation of open loop transfer function using this. So now since the unity feedback is there, the closed loop transfer function, will become 10 into, of course, again just to clarify, the closed loop transfer function is given by GFS by 1 plus GFS into HFS. If you do this, this divided by 1 plus this will yield this. This is S plus 3 divided by S plus 6 into S plus 1 plus 10 into S plus 2 into S plus 3. So where are the zeros? Zeros will still remain there. You can see zeros will be there at the same point, whether you open the loop or close the loop. So this is what we are supposed to take out from open loop to closed loop. The difference of zero position from open loop and closed loop is absolutely same. So there is no movement, but poles will certainly move depending on what is this value and what is this value. So let us see what is the pole position when you add a 0 to this. So what is this? So I need to solve for this. So it will become S square plus 7S plus 6, and it is I think it is 10s square because 10 is there, and you have this 5s means 50s plus, and you have this 6 into 10 is 60. So now the denominator will become 11s square plus 57s plus 66. So this is what the denominator. So once you know the denominator, I can find the closed loop poles. This is what closed loop poles. The roots of this denominator equating to 0 will give you the position of the closed loop poles. So I can now do that. So it is now of order 2. It is 1 degree is 2. It is now 11, 57 and 66. So now it's at minus 1.74. 6 is one pole. How about the other pole? Other pole is at minus 3.43. I hope it's a real value. It's a real value. Now carefully try to understand what happens to this pole. This pole which was there at minus 1 before the closure of the loop, after closure this goes to minus 1.746. How about this? This was there at minus 6. Now it is coming closer to this. So it is now at minus 3.43. You can see they were actually in the real axis. They continue to be in the real axis. Now they are coming closer to 0. They are coming closer to 0. Make out? They will never become complex. In the previous case, when there was a pole added at minus 8, the poles were becoming complex. Do you see this? So this was becoming complex. when you didn't add anything, this is slightly moved here. This was actually going away. Now the moment when you added a zero, now it is going closer to this. Fine. Of course, it is. We are trying to understand something out of this. Let me just give a bird view of all these things. What is one very important observation? Very important observation is zero's position. Zero's position will not change. That is, for open loop transfer function or closed loop transfer function, they are at same point. Correct? They are at same point. What is the second observation? The second observation is that you can just carefully note, just note one important thing. What is one important thing that you are trying to see here is just see the movement of this pole. See here, was this -1 -6? Was this -1 -6? Was this -1 -6? Were these are the closed loop, open loop pole positions, whether you added a pole 0 or whatever. See here, I just want to show this. This was there at -1, -1, -1. So -6, -6, -6. They are there. So let me just hold this so that you can able to make it. So this is what. Now this is what is the observation we have to make here. Let me just see this -1, -1, -1. Just have a look at this -1. See now, this is open loop position. When you close the loop without having any pole at 0, can you see this is moving closer to this -2? Can you see this is also moving closer to -2? Can you see this also going closer to -2? Meaning to say, this was the open loop pole position, -1, -1, -1. And it is going closer to this. This is going closer to this. This is going closer to this. Now, this is when this is 10 here. You have 10, 10, 10. What you can do is, for curiosity, make this 100. Make this 100. Make this 100. You will certainly see this will be moving closer to -2. Forget about this. This will be moving closer to -2. This will be moving closer to -2. This will be moving closer to -2. Meaning to say, the open loop poles will go towards the 0 position as they are closed, as they are becoming closed loop. Meaning open loop poles will go closer to open loop zeros. Correct? See now, there was of course, in this case there was a pole at -1. This -1 is going closer to -2. Now you can see now it has gone to, whether you add a pole or 0, whatever the case is. So this is consistently happening. Can you see here? This is going closer, this is going closer, this is going closer. So meaning to say, in control system, all open loop poles will go to 0 position, if at all, if there is a 0, See now here, this is how anyhow going. How about this? It doesn't have a 0 anymore. But so just carefully listen to me here. If there is a finite 0, in the transfer function which is there at -2, this pole will go here. Where does this pole will go upon closure of the loop? It goes to a 0 which is there at infinity. which is there at infinity. I just repeat, this pole which is there at -1 has to settle down in one of the 0 which is there at -2. Assume that you don't have second 0, because this also has to settle down to a 0, no, but this 0 doesn't find a 0 in the finite value. So then where it should go? It should go in search of a 0 which is there at infinity. So which is there at infinity. You can see it is keep going here. This is the case for all transfer functions. Let me again repeat. A open loop pole will go to closer to a open loop 0. Let me say open loop finite 0. If there is a finite 0, what is the third one? Open loop poles will go closer to a 0 at infinity. So these are all happening upon closure of the loop. A open loop pole will go closer to 0, which is at infinity. See here, where are the zeros now? One 0 is at -2, other 0 is at infinity. Correct? So where does this will go? This will go closer to this. Where does this will go? This will go to that infinity, which is there. That's why it's keep going here. Come to this. So where is this? Can you see this one? Is it not going here? But how about these two poles? They are actually going here and going here. Where they are going? They are actually going to infinity. So this is actually going. Infinity need not be there on the real axis. It can be here or this way also. So it is keep going. It's keep going here. So now, since there is a finite 0, it will terminate there. Since there are two poles, but the zeros are not there at finite. So where is the 0 now? There are two zeros at infinity. So that's why they are going to infinity. Come to this. How many zeros and how many poles are there? You have -1, -6, -2, -3. So can you see these two are the 0 portions? So where does this pole will go now? It has to go to a 0. So do you have equal number of poles and zeros? So that's why this pole is going to this 0. Sorry, can you see? This is going to this 0. Can you see this is going to this 0? So now they are not going to infinity, because you have its pair is here. Whereas in these two cases, you had this pair. Where is the pair of this? Its pair is there sitting at infinity. That's why they are going in search of that. How about this case? So this has got its pair. Where is its pair? Its pair is at infinity. That's why it's keep moving. So in control system, poles and zeros are always coming in pair. That pair, assume that you have this. Let me just write. Suppose this is transfer function, which is 10 into s plus 6. This is s plus 1. Assume that this is 100. So where is the poles and zeros? So it's at -1 and -6. Upon closure of the loop, what will happen? This will certainly come close to this -6. When this is 100, it may be here. When this is 1000, it will come closer. When it is 10,000, this will much more come closer. When does this is exactly sitting at this point? When this is infinity. When this is very, very large, maybe that we can just do that. So what is closed loop transfer function? Closed loop transfer function is 100, or let me say it as k. Let me put it as k into s plus 6. Shall I write it as s plus 1 plus of k into s plus 6? So then what is this? Is it not k into s plus 6 divided by s plus 1 plus of k s plus k6? So then what will happen to this? It is k into s plus 6 divided by, what is this? If I take out k outside, is it not 1 plus k plus of what? What is this? Correct. Now keep giving value of k. K is equal to 1, 10, 100, 1000, 10,000. What is the position? Correct. If I take k outside, so does this become okay, forget about this. So this k will be, if I just take this outside, this is s plus 6, so I'll take this 1 plus k outside, then is this k6 plus 1 by 1 plus k. So is this now k by 1 plus k? This is s plus 6, and this is what? s plus k6 plus 1 by 1 plus k. Correct. Forget about this. Where is the pole position? So what is pole position for k is equal to 1? So what is k6 plus 1 by? So I'll just do I'll just put that alpha a. So I'll make this, of course it is bit involved. It is alpha a into 6 plus 1 divided by 1 plus alpha a, close, calculate for a is equal to 1, it's at 6.5. Calculate for 10, it's at 60. Of course this is pole position is minus 60. Calculate for 100. Can you see, is it 600? Calculate for 1000. It is minus 6000. It is minus 60,000. What is that we are trying to? What is something going wrong here? Just a minute. One sec. Just a minute. So is this fine here? K plus 1, this is okay. This is also okay. Is this fine here? It's also fine. So fine. How about this? Let me just check out. Oh, there is a problem in this equation. Wait, it's not correct. So I didn't put the parenthesis properly. Let me make this one sec. That's what. So it is this is the equation I have to put. It is open the parenthesis, alpha a into 6 plus 1, close the parenthesis, divide by 1 plus alpha a, close, and then now calculate for k is equal to 1. It is minus 3.5. For k is equal to 10, it is minus 5.54. So this is due to a wrong entry of my equation onto Calc, and now it is for calculation of it is minus 5.95. Next calculate for 1000, it is minus 5.9. It is very interesting to observe as the value of k is increasing. See now, this was your pole position, which is there at minus 1 when you open the loop. When you close the loop, and when the value of k is equal to, maybe you can take the value of k as 0.01. So now I'll just do 0.01. Can you see it's at minus 1.04? So this k value starts departing from this minus 1 as the value of k increases. As the value of k increases, this started moving out of this position. You can see as the value of k increasing, can you see it is becoming minus 1.04, minus 3.5, minus 5.554, minus 5.95, minus 5.99. If you make this as 1 crore, even then it is minus 5.9999999. What I mean to say is, this pole which is there at minus 1 will go and occupy this as minus 6, that is it will going to occupy the 0 position where this k is equal to infinity. Only when k is equal to infinity this will become equal to minus 6. What I mean to say is, all open loop poles will settle down at 0 position as the value of k tends to infinity. If the value of k is 0, where are the closed loop poles? The closed loop poles will be sitting in the open loop pole position only. That's what. When k is equal to 0.01, which was there here, suppose the value of k is 0.00001, it will be at almost minus 1.000. The whole summary of this is the movement of this open loop pole upon closure of the loop. Upon closure of the loop, if there is a zero available, this open loop pole which will become closed loop upon closure of the loop will move towards where? Will move towards an existing 0. If there is no 0, then it will be keep finding out the 0 position which will be there at infinity. So now we can take another example where you have, so assume that you take another example where you have this as some k by s plus 1. So this is your open loop transfer function. What is the closed loop transfer function? Closed loop transfer function is k by s plus 1 plus k. So then what is this? Is this not k by s plus k plus 1? So now as the value of k is ranging from 0.01, 0.11, 10, 100, 1000, 10 power 4, 10 power 10. What is the pole position? Pole position is at, what is this? Minus 1.01. This is minus 1.1. This is minus 2, minus 11, minus 101, minus 1001. So this is minus 10,001. Where it is moving to? This is your pole position. The earlier pole position was there at minus 1 when it is open loop. Now as the value of k increases, can you see it is keep moving, keep moving, keep moving. Where it is moving? It is moving towards minus infinity. Why it is going to infinity? It is going to infinity because it's an imaginary 0 is sitting here. Where is the 0 sitting? The 0 is sitting at infinity. There is a 0 sitting at infinity. When you don't have a finite 0, then where is the 0? 0 is at infinite. So this is a very crucial thing in control systems. Always the poles and zeros will come in pair. If you have a finite 0, then this open loop pole will go and settle in that 0. If the 0 is not there at finite value, then it is there at somewhere infinity. So it can be on the imaginary, it can be complex, it can be over here on real axis, whether it can be plus or minus. So it will happen like that. So this is what is interesting thing. So this is what I wrote. Zero's position will not change whether it is open loop or closed loop. Open loop zeros will go closer to open loop pole position upon closure of the loop. Again, open loop poles will go to zeros at infinity if you don't have any finite zero. So this is what the case. You don't have a finite zero at all. So when you don't have a finite zero, then where does this pole pole will go? Pole will go somewhere. It will go to a position which is to infinity, because there is a zero sitting at infinity, because it doesn't have a finite zero. It doesn't have a finite zero. So that's about the movement of poles as the value of gain changes, and what is the pole position change. Okay, what is the impact of pole position if you add a 0 or pole to the existing system. So that's what let me just try to ask you do some. This is your transfer function. You tell me what will be the pole position if you have this at s plus 2 and s plus 4. So give me open loop transfer function as well as closed loop transfer function. Let us know the pole position. So this is, anyhow it is straightforward. Open loop pole position, it's at -2 and -4. Where does these poles may go? They have to go to infinity. Because it doesn't have its pair on a finite point. You can see that there are no zeros which are there finite. Where are zeros now? Zeros are at infinity. When zeros are at infinity, as the value of this 100 is there, 10,000, whatever comes, now this will be, you can just give me what is the closed loop pole position. And it is interesting to see the pole position will have a real value -3 plus or minus jx. You give me this x value. This is, anyhow it is -3. Just to verify that whether you are getting the closed loop transfer function, which should be now 10 divided by s plus 2 s plus 4 plus 100. Will it not be 100 divided by s square plus, how much is this? This is 6s plus 108. What are the roots of it? Is it not -3 plus or minus j? For that, let me just use my calci. So it is now, this is 1, 2, this is 1, 6, 108, 08. Can you see it is -3 plus or minus j 9.94. This is now the poles have, of course you can see it's exactly the midpoint of these two. So midpoint of these two is -3, so that's why it is moving here. If this value of 100 becomes 1000, then this becomes 1008. When that is 1008, you can see what happens to this. Suppose, let me just make it 1008. What are the pole position? Can you see this is still -3? This will be still -3, but the imaginary axis will be, sorry, you can see it is plus or minus j 31.60. Can you see this is now moving out here? This is what the open loop poles, the closed loop poles have come here. If I further increase the value of k from 100 to 1000, it will go here. If I make it 10,000, then this will become 10,008. It will further go here. If you make it 1 lakh, it will further go here. Where they will go? They will go to infinity. When I say infinity, that is complex, negative, positive, doesn't matter, because infinity is infinity. So they are actually going here. But the real axis, or the real part of that pole position, is -3, which is exactly half of these two pole positions. Would you be able to get this concept? The main thing it is, a open loop 0 will have to settle down in a 0. Where is the 0? 0 can be a finite value of the transfer function. If there are no finite values, then it has to go and terminate in infinity as this becomes infinity. If it is finite value, then you can see this is sitting here, this is sitting here, this is sitting here. As the value of this k increases, then the pole position, closed loop position is moving towards infinity, Hope okay, this may be slightly intense one, but it is not difficult. Just let me know how the things is that fine? Okay, I hope it's not a big difficulty. Thanks for that. Okay, let us just thanks for the response. Let me move on. So if I move on, this is what is we are just looking into. Now, why we are so much worried about this closed loop pole position? So, no, why? What is the reason behind worrying so much about the pole position, whether it is there at infinity, so on, so on, so. And we will also see one more interesting thing. So we will also see if there is a zero lies to the right hand side of the S plane, what happens. So let me take, I was keep telling no, a open loop pole will go towards the zero wherever zero is sitting. So let me just take this transfer function. So this transfer function is this number is, let me just track that number. This is 7, this is CS8, this is CS9. So assume that I have a open loop transfer function which is 10 into s plus 1 and s minus 4, and let me just take this is s into s plus okay, let me just take it at s plus 6. This is 6, this is 4. Fine. Where are the poles now? Poles and zeros. This is at the origin, this is at minus 4, this is at minus 6, and this is at plus 4. Am I correct? Of course, by this time, so I should be very comfortably representing the poles and zeros on my S plane, which is pretty easy. You're representing at the origin, you're representing at minus 4, you're representing a 0 at minus 6, you're representing a 0 at plus 6. So now what is closed loop transfer function? Closed loop transfer function is 10 into s plus 6, s minus 4, and this is s into s plus 4. What is this? Plus of 10 into s plus 6, s minus 4. So shall we solve for this? Okay, anyhow this is same. So this will remain as it is. In the denominator what I have? It is a square plus 4s plus 10 into, is it now a square, and can I see now is it 2s? It is plus 2s minus 24. Correct? This is actually plus, okay. It is now s square plus 4s plus 10s square plus 20s minus 240. Correct? So then is it actually 11s square plus 24s minus 240? Correct? Can I find the roots of it? If I find the roots of it, where is my calc? So my closed loop transfer function is 10 s plus 6 s minus 4. This is now of course it's actually 11s square plus 24s minus 240. What are the roots? Roots are 11, 24 and minus 240. The roots are, you can see it is a real root, 3.70, and other one is minus 5.7 minus, okay. So now can I write this as 10 into s plus 6 s minus 4, and this is s plus 5.88 and s minus 3.73. Correct. Now it is interesting to see I had my zeros at -6 and +4. What was said? This pole which is at origin and -4 will go and terminate at this point. They go closer to this. Now you can see, has this -4, has it come to -5.86? Can you see, has it come here? This is -5.88. This pole, which was the open loop pole, has become this position when you close the loop. Upon closure of the loop, it has come here. How about this? This was there at origin. Now it has gone to right hand side. So what is this? This is now sitting at 3.7. These are 3.7. Is it not interesting? What is interesting, what we are supposed to note here is this pole has moved towards right side, whereas this pole has moved towards left side. Why it is moving to right side? Why it is moving to left side? Because its pair is sitting here. Its pair is sitting here. It actually going in search of its pair, that is its 0, which is at -6. This 0 is there at +4, so that's why it is moving there. If this 10 becomes 100, this will go much more closer. This will go much more closer. If this becomes 1000, this will give much closer, much closer. When this will be sitting at -6, when this is infinite. When this is sitting at +4, when this is infinite. Meaning to say, all open loop poles will settle at zeros as the k value tends to infinity. This is if there are zeros, finite zeros. If there are finite zeros, it goes there. Otherwise, where does this poles will go? Poles will go to infinity. That's what was happening in the previous case. Can you see in the previous case what was happening? Because there was no there is no pair, so where they are going? They are going to infinity. But it is finding its 0 there, it's going here. It's finding its 0 there, it's going there. Fine. Now again, the basic question comes, why we are so much worried about this poles, closed loop poles? Because that will decide the stability of the system. Now comes the stability of the system. Why we are so much worried about? Because in the entire 1 hour time, we are stretching our head like anything. Where does this pole go? Where does this 0 go? Where is the 0? Where is the pole? If you add a pole, what happens? If you add a 0, what happens? We are just going mad with this pole position. Why this pole position is so important? Because that closed loop pole position will decide the stability of the system. Maybe in the yesterday's class, in the yesterday's what is that simulation. So let me just show you this. So in this simulation, you can see when the gain is when the gain is how much? So when the gain was like, let me just make it 1500. So it was acting like a pure amplifier. So this is, can see this is an amplifier. So let me just take out the other thing. Let me just take out this. Let me again run. Let me see the input here and then output here. Can you see the output is amplified one? That's perfect. Now it's a stable circuit. The moment you make this 2000, the moment you make this 2000, now the system is becoming oscillatory. It is not stable. Can you see the system has lost its stability? Because what do you mean by a stable system? It was said to be stable you are actually supposed to get same 100 hertz signal. If you're giving a sine wave of 100 hertz, so what you're expecting is 100 hertz signal with some amplification depending on the amplification factor. That is what is a stable system. But for a certain value of R2 which will make certain gain, for that point what you are having a system is totally behaving totally differently. Now it is acting like an oscillator. It is not a stable system. Suppose if you make it much more larger, assume that I make it 3000. If I make it 3000, just imagine what happens. Can you see it is clipping off? Can you see it is, okay, if you can see here, the waveform is going up to saturation. It's going up to saturation because I have a plus 15 volt. It's going up to 12 point or maybe 13 volts where the outputs are saturated. You can see output is saturated here. So output is saturated. So when you see output is saturated, now you're not getting the intended thing. What was the intended thing? If you can actually find out the frequency of this is nowhere close to 100 hertz. You expected this circuit to amplify. Now it is oscillating. Meaning to say, what we are trying to do is, so the system stability will be lost if the closed loop poles are not there in certain region of the S-plane. This is your S-plane. This is your, of course, we will get to know that a system stability. So now you have a system. You have an input. You have an output. So when do you say system is stable? Maybe you might have learnt in your signals and systems and so on. So if you give a bounded input, assume that, okay, I'll just give a bounded input. A delta function is a bounded input and this step signal is a bounded input. Okay, now this is with respect to time, this is u of t, this is delta of t. What is this delta of t? Delta of t is equal to 1 at t equal to 0, and it is equal to 0 for all values of t other than 0. Correct? This is how you define a delta function. A delta function has got a magnitude of 1 at only t equal to 0. For other values of t other than 0, its value is 0. So this is called as a bounded input. Matlab, its magnitude is bounded, and as the value of t is tending to infinity, you can see output is a finite value. See here, is this a step function? This is a step function. As t tends to infinity, is the magnitude constant there? So you have a finite magnitude. Of course, it need not be constant, but it's a finite magnitude. Is this sine wave a bounded input? Is it a bounded signal? A system is said to be bounded if at all as time tends to infinity, its magnitude should be finite. Suppose assume that you make t is equal to infinity. At t is equal to infinity, do you have a sine wave? Which is keep continuing? Is the magnitude finite? In such case, we call a unit step input, a delta function, a unit step input, a sine wave as as bounded inputs. Bounded input. What do you mean by bounded input? Whose value is finite as t tends to infinity. Suppose if you give such type of bounded signal as the input, if the system is stable, the output should also be a bounded one. Then only I'll call the system is stable. A system is stable if the input is bounded. If you are applying a bounded input, if it results in a bounded output, then you say system is stable. Meaning, if I give a step input, suppose if the output is like this, is this a stable system? Yes. So because the input is bounded, at t is equal to infinity, you have a magnitude. So this is your output. Output is also bounded because its value is 0 for a certain, for t tending to infinity. For t tending to infinity, what is the value? It is 0. Is it not finite value? Or assume that you have output which is going like this. For this input, you are having this output. So what's happening here? Is this not a finite value? This is a finite value. So now, when does a system is stable? A system is stable if the, for a bounded input, if the output is also bounded, then such system is called as stable system. When does this will become unstable system? For a bounded input, if the output is unbounded. If the output is unbounded, then you say system is unstable. Assume that you are given a step input. But assume that if the output goes like this, so assume that this is your output, this is your input. Is your input bounded? It has got some x value constant, which is for t equal to infinity also it is some value. So now this is your output. So as your t is keep on increasing, this is keep increasing, As this t tends to infinity, what is this value? This is also infinity. So this is a unbounded output. Input is bounded, but output is unbounded. I'll call it as unstable system. A system is said to be unstable for a bounded input if the resultant output is unbounded. I call it as unstable system. Now you have stable system and unstable system. Next, in between them, I have a critically stable system. It's like on a pendulum. Supposing that you have this peak. Suppose if you put a ball on the peak of this structure, there is no guarantee that, assume that if this is stable and this is unstable, this ball can either fall here or fall there. So this we call it as critically stable system. In this critically stable system, we end up with oscillations. So that's why this circuit will be in, suppose if I just make it equal to 2000, if I make it equal to maybe 1500, if you run it here, the system is stable. The moment you make it 2000, the system is critically stable or oscillatory. When it is oscillatory, the system will break into oscillation. So it is very interesting to see, even if you take out this input signal, if you make your input signal 0, even if you make your input signal 0, you'll be still getting the oscillations. Can you see? Are you still getting the oscillation even without input? Can you see? This is, you still have the oscillations. This is what is the beauty of oscillators. Suppose if I make this 1500 and run, see the output? Output is 0. See here, microvolts, 150 microvolt, output is 0. 0 matlab there is no sine wave, because input is not there, that's why output is also not there. If I give the input, it will come. Suppose if I make this oscillatory, without input, you will get the output. That's why students, whether you remember or not, we used to always say that for oscillators, for signal generators, never put the input, never indicate the input. Meaning, we used to say, no, if it is an oscillator, does an oscillator require any input? The oscillator doesn't require any input. So that's why we were so critical whenever you assume that maybe in the previous AEC class, you had an oscillator, which is now minus plus. Assume that you had a square wave oscillator, square wave generator. It's an oscillator. This is down here. Can you see now? This is so and so. We were so critical. You are not supposed to put any source here. So it doesn't require any source. So that's why whether it is a square wave generator or a sine wave generator, input is not required. So that is the beauty of a system. A beauty of a system without input, without zero, without any input, you'll get the output. That is possible only when the system is critically stable. Critically stable. If the input is suppose the system is stable, it needs some input. So for critically stable system, it doesn't require any input. We call it as an oscillator system. So basically what we are trying to do is the system stable or not, or critically stable? So how do we get to know whether the system is stable or not, or critically stable? There comes the pole position. There comes the pole position, the closed loop pole. Because every system will have a closed loop transfer function. If the closed loop transfer function has poles to the left hand side of the S-plane, the entire left hand side, then system is said to be stable. If the poles come onto the right hand side, then system is said to be unstable. What poles? Closed loop poles. If the poles are there on the imaginary axis, if they are sitting here, then it is called as oscillatory or critically stable. Now you get to know why we are so much worried about the pole position. If in a S-plane, if you have poles anywhere on the left hand side of the S-plane, this is left hand side of the S-plane, no? This is left hand side. Let the pole be there anywhere, system is stable. Even if you have 1000 poles over here, if one pole comes here, then system will become unstable. We'll see why it is happening. So suppose if one comes here, it is unstable. Even if thousands are there, all poles have to be there on left hand side for it to be stable. If one goes to right hand side, system is unstable. For system to be oscillatory, you have to have a pair of poles coming on imaginary axis. One cannot come on imaginary axis. It has to be always pair. So this is critically stable. So what is the whole story? The whole story is, for a system to be stable, all closed loop poles should be onto the left hand side. Even if a single pole go to the right hand side of the S-plane, single closed loop pole go to the right hand side of the S-plane, system is unstable. If minimum two poles are coming on the imaginary axis, system is critically stable. So this is because we are so much worried about whether it is there on the left hand side, right hand side, or on the imaginary axis. So that's why we are giving so much of importance to closed loop pole position. So that's why we are just looking at, does the addition of a pole or a zero or changing the value of gain, what happens to your closed loop pole position? That's why we're just so much worried about where it is going, whether it is coming onto right hand side, left hand side, is it going towards infinity, where it is going towards right, left. So that's why the entire control system, we deal about stability. When you say stability, it is the position of closed loop pole, whether it is there to the left hand side of the S-plane, right hand side of the S-plane, or on the imaginary axis. That's it. That's the entire story of your control systems. You are looking at where are closed loop poles. That's it for the day. Thank you so much for being with me.